All right, we're going to start chapter 5 today, early atomic theory. Again, how do they know about these little atoms? Because obviously you can't see them. So there's a lot of people that put their information together and came up with some ideas of what's going on. Here they talk about lightning. Really what lightning is when the clouds rub against each other, if you've ever walked across the carpet and zapped somebody on the nose, static electricity, it's a buildup of electrons. Okay, it's kind of the same thing on a much larger scale, and your rubbing is the clouds rubbing against each other, and then you get this buildup, and the only way to neutralize it is to discharge it, and that's those lovely lightning bolts that we see. Okay, so when we first started talking about um, atoms, these little particles that make up everything, it was kind of the crazy Greek guys, the ones wearing togas and drinking wine or something. I'm not sure, but anyway, they came up with some ideas. The first guy, Empedocles, I don't know. He's the first one that said everything's made out of elements, and he said the four elements were earth, wind, fire, and water. He said that was it. So, but he's the first one to start classifying things, and then you had Democritus, and he was the one that said, wait a minute, everything's made out of these little tiny particles, and he named them atoms. So he's the one that came up with the name for atoms. And excuse me, the word atoms means, it's a Greek word because that's what Democritus was. It means indivisible. I think I covered that up with me. Sorry. I'm having a hard time where to stick myself so I don't get in the notes, but you got me over here this time. Anyway, Democritus said everything is made up of little tiny particles you can't divide anymore, and those are atoms. Okay? Well, then this guy came along. His name was John Dalton, and he had to be brilliant because he was a chemistry teacher. I mean, let's face it, Dalton, what he did was he didn't do any work himself, but what he did was he took all the information from all these chemists and scientists and whatever and started putting it together so it made sense. So he wrote what they call the atomic theory. And what's really cool about what he did, look, 1810 is when he finished it. What he said is, hasn't been proved wrong now. So kind of a smart guy, but again, chemists, so we're, smart people. Anyway, what he said was elements are composed of little tiny indivisible particles called atoms, which Democritus kind of said too. And he said atoms are actually made up of smaller particles as well. Well, Dalton did, but this is what we found later. The smallest particle that has all the characteristics is an atom, but we actually find smaller particles in atoms as well, like protons, electrons, neutrons. Then he said that if you have an atom of the same element, they're alike in mass and size. They're off a little bit, but really what it means is all the hydrogen atoms are the same. All the helium atoms are the same. Okay? He didn't know about isotopes. I don't think have we talked about isotopes? Isotopes are a little bit heavier, a little bit lighter. But again, he is pretty spot on. And then what he said is atoms of different elements have different masses and sizes. Okay, so all the hydrogen atoms are similar to each other. They're the same. But if you compare a hydrogen atom to a helium atom, they're not the same. Okay, so he said if you have a different element, they have different masses and sizes. Okay, and again, that happens a little bit. Sometimes there's some that have the same size, like carbon-14 and nitrogen-14, but they're different atoms because they have different protons, and so there's a little modifications that have been made to them, but like I said, he did it in the early 1800s, so it worked out well. Okay, he also said when you take atoms from two or more different elements and they chemically combine, you end up with compounds. Here we have an example of water. Okay, so you can take different elements, and if they chemically combine, now you have compounds. They don't make up atoms anymore. What they really make up is molecules. Okay, he also said that atoms combine to form compounds in simple numerical ratios. In other words, water is always H2O. It's not H2.5O2. They're always whole number ratios. They don't combine a little bit. There's no fractions. There's no percentages. It's either a whole number or not at all. Okay. And then he said atoms of two elements may combine in different ratios. Here we have the example of water, which is H2O. And then we have hydrogen peroxide, which is H2O2. Okay, another hydrogen in there. Okay, they can do this, and where you'll see it the most is with like carbon compounds. You can have CH4 You can have C2H6, you can have C3H8, all these different carbon compounds, and they're carbon and hydrogen, but because they combine in different ratios, they're different compounds with different substances. You look at water and hydrogen peroxide. They're both clear liquids, but you definitely don't want to take a swig of this when you're really thirsty. So they have different compounds. They have, they react differently with things. They're different compounds because they're different ratios. Okay? And again, one of the things that came out of Dalton's is what they call the law of definite composition. All right? What it says is a compound always combines the elements, two or more elements, how many elements it has, and they always have to be in the same proportion by mass. In other words, the ratio has to be the same. Okay? Here we have in water, 11.2% is hydrogen and 88.8% is oxygen. This is by mass. Okay? So if you look here, it has to be in this proportion. If you change the proportion, in this case 5.9 to 94.1, this is no longer water. This is hydrogen peroxide. So if you mess with the ratios, you have a different substance with different properties. It might not even exist. That's the other thing. Okay, so the law of definite composition says you have, when you combine two or more elements, if you have a compound, the proportion of the elements always has to be in the same, or the mass has to be in the same proportion. Sorry, I said that wrong. Okay, if you change the proportion, you have a different substance with different properties. Okay, here's some more. You don't have to worry about it so much, but here's two compounds, copper 1 chloride and copper 2 chloride. Okay, these have different, what they call oxidation numbers, and they are different compounds. They look different, they're different colors, they react different, they have different percentages. Okay, because here in copper 1 chloride, which is CuCl, you have 64.2% copper. If you go to copper 2 chloride, it's only 47. So if you're looking for a compound with a lot of copper in it, you'd want to go with this before you went with this. Here I was talking about with carbon and hydrogen. Okay, just here we have CH4, which is methane, natural gas. People burn it for energy. It's what you see when you go by oil wells. You have that little flame going out. That's natural gas, CH4. You can see a lot of it's carbon. 3/4 of it, 75% is carbon, 25% is hydrogen. But if you become C8H18, this is octane, which is your gasoline you put in your car. Look how much more carbon it has in it. Okay, so even though they're made out of the same stuff, different proportions, different substances with different properties. Okay, so when we're talking about, a lot of the stuff we're talking about is theories, but there are some laws. Okay, a law is something based on behavior, observed behavior. Okay, you can't modify it. If you remember a theory is when you do an experiment over and over again, you get kind of the same results. So you start coming up with theories like his atomic theory. Some things have undergone modification. But a law, like definite composition, that never changes. So laws are rules or scientific things that don't change. Other examples would be the laws of motion. Okay, they're not testable. I mean, they are testable. I shouldn't have said it that way. They're something you observe that always happens. It's always the same. Whereas a theory is based on research that you do, and you come up with an idea based on the research that you did. Okay, so a theory is behavior explained. Like again, Dalton's atomic theory was him looking at a bunch of information and trying to organize it. It can be modified, and some theories have been tossed away. They were wrong. Okay, so theories can change, laws cannot. Okay, all right. Which of the following statements in Dalton's atomic theory has been modified or discarded? Okay, atoms of the same element are alike in mass. Chemical compounds are formed by the union of two or more. And I'm really sorry I'm in the way. The last question says atoms combine to form compounds in simple numerical ratios. Well, these two are. This one has changed because they can be a little bit lighter, a little bit heavier. They're called isotopes. Okay, and we'll talk more about those later. Okay. Okay, which pair of formulas illustrates the law of multiple proportions? In other words, they have to be the same thing, but we have to have different numbers. Well, those have different compounds. Those are the same thing. Those are different compounds, so it would have to be this one. Okay? Because law of multiple proportions, your same elements, just in different proportions. And I don't really know if it happens with sodium, but with carbon and hydrogen compounds, it happens a lot. You can have millions of different compounds made of the same two elements, just in different proportions. Okay? All right. Now, when we're talking about atoms, remember atoms have the same number of protons and electrons. But if you remove some of the electrons or you add some electrons, because they can do that, they're on the outside, they're not real close, it's easy to move electrons around. You can come up with what they call ions. And really what an ion is a charged particle. So if you take a metal and you take away a couple of the electrons, what happens now is it used to be neutral. The protons and electrons equaled each other. But if you take away some electrons, you take away some negative charges, what's going to end up happening is you're going to have what they call a positive ion now. Okay? So these charged particles are awesome because what they do is they conduct electricity. We use these in a lot of things. Your car battery has sulfuric acid in it and some water. Because of that, it conducts electricity through it. If it didn't, then your car wouldn't start when you hit that key or push the button. Now most of us have cars where we push the button. Weird, right? Anyway, it's important to have these ions because they conduct electricity. And the guy that discovered them was Michael Faraday. He's more of a physicist, but the term ion came from thousands of years before. It's a Greek word and it means wanderer. So they thought because the electrons kind of wander around, that's why they call them ions. But an ion is a charged particle. And it comes from taking an atom and either adding electrons to it or taking away electrons. And because now you don't have the same number of protons and electrons, you have a charged particle. Okay? Svante Arrhenius, this guy liked to work a lot with acids and bases, but he's a chemist, so he liked to mess with stuff too. He said an ion is an atom carrying a positive or negative charge. Okay? We have positive ions, we have negative ions, and they're present in a compound. If it's molten, if you dissolve it, change it from a solid to a liquid, and it conducts electricity, then we know there's ions present. Okay, that's what he figured out. And actually, like I said, he worked a lot with acids and bases, and that's common in there too, because when you're talking about an acid or base, something happens with water that produces these ions. Okay, now when you're working on them, a cation, remember, is a positive ion. It moves towards the negative electrode. And again, opposites attract. I don't know if it happens in human relationships, but it happens in ions. A positive ion is attracted to a negative electrode. And they actually call the negative electrode the cathode, I suppose because the cations are attracted to it. So the negative, the anion, and again, I'm sorry you can't see that totally, but an anion is a negative ion. Well, it's going to move toward the positive electrode, and they call that an anode. And if you think about your car battery, you have your two charges on there. Excuse me. You have to hook up your red and your black. The red, the positive electrode on your battery is called an anode. And then the other one, the negative electrode, would be your cathode. And they attract opposites. Okay? And here you can see it. Okay, so now we have atoms and we know they exist, but we had people that started realizing that actually atoms are made up of these little particles. The first guy that discovered anything about electrons was a guy by the name of J.J. Thomson. No P. I don't know, he lost his P in his name, but 1897. So this is almost 100 years after Dalton starting to figure out we got these atoms. He used a cathode ray. These used to be the things they used to put in TVs many years ago. But what they found out was that he could move this flow of electrons. It was attracted, positive and negative. He could move the stream. So he figured, you know what? Because I can interfere with it, because normally it travels in straight lines. But if I take electrical fields or magnetic fields, I can actually move this beam. So there must be some different charges involved in there. Okay? And what he gets credit for is discovering the electron, because he'd take a positive and it would be attracted to it. So we knew there was a negative charge here. So there had to be something going on with this flow, and he decided that they were he called them electrons, and that they were negative, which he was right, because again, if he took a positive